Very good. So today we're going to talk about doing input and output in Haskell. So Haskell is a purely functional programming language, which means every function is pure, which means there are no side effects. If you call a function, nothing gets mutated outside of that function. It just takes some arguments, does some computation, returns a value. So if everything in Haskell is a pure function, then how on earth can you do input-output? Well, we're going to figure that out today. So first, I'm going to briefly mention development environment. Then we're going to talk about input-output primitives, how you basically write hello world in Haskell. We're going to discuss how that actually is interpreted. And then we're going to proceed building a very small application using input-output. And we're going to do some stuff, discuss how to do this interactive loop, how to manage state, how to do sort of list of actions, et cetera, et cetera. And then in the end, what we will come to is a version of our program where we essentially separate the part of the program where we are able to do some input output from the other part of the program where we only have pure functions. Okay, now everything is going to be pure, but some functions are going to be sort of marked as input output and others will not. Okay, so development tools. So I've asked you all last week to install Haskell because we're going to be using this today in the labs. Right now in the lecture, it's not important. But if you haven't downloaded Haskell yet, you have about an hour. Well, some of you have more before the lab to actually properly install Haskell. So go to haskell.org/downloads, follow the instructions at the top of the page, okay? Install Haskell, make sure it works for you because it will be important for the lab. Okay, so the development environment, I mean, everybody has their own development environment. You can use Visual Studio Code, or you can use Sublime Text, or you can use whatever your favorite text editor is. Mine is Vim. This is how I typically work. I just have I work in a terminal where I have Vim. I have REPL, which is the redevelop print loop, right, the interpreter. And I have the GHCID, which is basically gives me an instant response whenever I change the code. So yeah, that's basically my version of an IDE. But of course, to each their own, and you can use whatever you want. So going straight into input and output in Haskell. So how do you do hello world? Well, perhaps unsurprisingly, hello world is very straightforward to write in Haskell. Now, the only weird thing is that instead of print, you have to write this put strlen, which is put a string with a new line at the end. It's a mouthful. It's a weird abbreviation, but this is what we are stuck with in the standard library. So what's important for us is that this type IO with the empty parenthesis, this is actually IO is actually a type constructor. So remember that we can define type constructors which are parameterized by certain type variables. So somewhere in the base library, you have this data type defined, which of course is the implementation is of course defined mostly by the compiler, not by an actual library, although you can imitate IO pretty well on your own. Anyway, so we have this data IO A. So this is a type constructor, and this A is a type parameter. And whenever you have a value of type IOA, it means that you have a value that represents an executable program that can perform input-output. And if you execute this program, then it will do this input-output and return a value of type A. Okay, does make sense? So a value of type IO something is not run this program, is not an instruction to the compiler run or to the interpreter run this program. This is actually sort of writing down the recipe of what you're going to do if you're going to run this, if somebody's going to run this. And of course, main is the special variable, right? Is a special definition. Main is what the compiler uses as an entry point. So main always has this type, IO with empty parentheses. And what the compiler does when it compiles your program is main gets compiled to an executable, right? And then main is going to be the entry point of your program. So we have this IO with an empty parenthesis. And if you remember, empty parenthesis is just the type of an empty tuple. Now, an empty tuple is not a very interesting type in that it only has one value, which is the empty tuple, right? Now, why is it used here? Well, the idea is that if you have a type like IO empty tuple, it means that you have an executable program that performs some input and output and returns an empty tuple. Now, obviously, empty tuple is not at all interesting, right? Now, this means that whatever is interesting about this value can only be the input-output effects that this program is doing. Okay, so in a sense, when you see IO empty, empty parenthesis, empty tuple, that basically means that you have a program that you would run solely for the purpose of doing those input and output effects. Okay, does it make sense a little bit? Okay, so what is the type of this put string with a new line? Shuh, shuh, shuh. Okay. Yeah, somebody said the type is IO. So I want to immediately say that IO is not a type. IO is a type constructor. So if you want to say a type, it is always IO of something. It can be IO of an empty tuple, or it can be IO of something else. Right, so this function, right? We see that this is a function that we apply to one argument, which is a string, right? A string literal. And then the result of this function is whatever main is. The type of main is IO of empty tuple. So that means that the type of this function is going to be a function that takes a string and returns IO of empty tuple. Okay? Now this is important to understand that this function is a pure function. It does not print anything on the screen. Okay? So what happens here? What happens here is that this function takes a string and produces a program. Okay? It does not do anything with the screen. What all it does, it produces a program that prints that string somewhere. But the string will not be printed unless you actually execute the program. Okay? Make sense? This is a big shift, in paradigmatic shift from all the other languages that you probably know. So again, a function takes a string and returns an executable program. The program that we return is executed, well, if it is put in main, for example, and we execute main, then of course this string will be printed. But the function putstrlen by itself does not print anything. It's just a pure function that takes a string and returns a program. Okay, so programs in Haskell are just regular values which you can manipulate. Okay, very good. So now, if you have two programs, say print something and then print something else, you can combine programs sequentially by using this special do notation. Now, do notation is, in fact, a syntactic sugar for something purely functional, but we're not going to go into the detail of how exactly it is a syntactic sugar. For us, this is going to be the magic notation that we're going to use to compose programs. Okay? So do, very easily, we say do one thing and then another thing. So, I mean, intuitively, this does something very straightforward. Just do one thing and another thing. But again, remember that programs are just values, and this notation, what it does, it composes two programs, right, to build a bigger program, okay? So again, it doesn't execute anything, it composes programs into bigger programs, okay? Now, what if we want to do some input as well? Well, this is an example of how we can do this. We print something like, what is your name? And then we have this weird line, name backwards arrow get line. And then we print something using the name. So how does this work? Well, first of all, get line is a program that returns a string. So its type is IO of string. Okay? When you execute this program, it goes into standard input, reads a line out of it, and returns it. Okay. Does it make sense? Do you need a minute? Yeah? Yeah. So getLine is not a function. It's a constant value, which is a program that if you execute this program, it will go to standard input, read out a line from there, and return that line as a string, right? So it is a program that you need to execute to get the result. Now, hopefully this sort of makes sense. Again, syntactically, you can see name backwards arrow get line as just save the result of this computation into name, right? However, so what is important for us is, first of all, getLine is really a program. So whatever is on the right of this backwards arrow has to always have a type, a program that returns something. Okay, so on the right, we will always have IO of something. In this case, we have IO of string. On the left, we have a name, a variable name, right, which we bound the result to. So if on the right, we have a program that returns a string, on the left, we're introducing a new name. Well, in this case, it's called name. And its type is going to be just string. So it's going to be string. Okay? So this is sort of a way to unpack. If you have a program that computes something, then you can extract the value from there, sort of, right? And then you can use it below. Yeah? No. No. So this is important that you need to run this get line, right? And then after you run it, you have the result, which you just give a name, and then you use it below. So it's not the same as where, it's not the same as local definition. Here, the order of programs that you execute matters, right? But a good question, yes. So again, name here is not a variable like in Python. Name here is an immutable variable. It's just a name, right? Which we give to the result of that program. And now we can use this name anywhere below. So once getLine is executed, we can use its result below. Okay. So in general, when we have do notation, we will have a series of expressions. Some expressions will be just execute something, like print something, or I don't know, do something else, launch missiles, send a request to the database, right? And other times we'll have a program where we want to also record the result of that computation. And in that case, we'll have this backwards arrow, and then we'll introduce a name, a variable, that we will be able to use in the code below. Okay? This is how do notation works for us. Importantly, the last expression that you have cannot be an backwards arrow expression. because, well, you will not be able to use this variable anywhere, right? And the result of the whole do block is the result of the last expression. Okay, so whatever the last program in the block returns will be returned by the entire block. Okay. No, so the backwards arrow is a special syntax for the notation. It introduces a variable, so it's like with lambda, right? It's a special syntax that introduces some local names. Okay, very good. So you can, like one way to understand do notation and this IO type constructor is via recipes. So imagine that you have sort of a recipe that tells you how to make a cake layer, right? In a multi-layered cake. And then you have a separate recipe for the frosting for that cake. Now, to make an actual cake, you need to prepare cake layers and you need to prepare frosting, right? And then you need to mix somehow them, like apply frosting, wait for some time, and the cake is ready. But the thing is that if you want to write that recipe and you want to reference other recipes, oh, you can definitely do that, right? And then in the recipe, you will just say, okay, prepare cake layers. And then you can let's just use this Haskell syntax in the recipe. And we'll just say, okay, prepare cake layers. Well, we now will refer to the result of that as layers, and prepare frosting and refer to the result of that as frosting, and then use somewhere below. Okay. So in the sense of the recipe, when you write down the recipe, nothing is executed, right? You're just composing recipes together. And now what you can do is you can take one recipe, take another recipe, and just put them one on top of each other, like staple them or glue them together, and say that this is a bigger recipe now. Okay, and that's something that you can do, right? So this is exactly what you can do with this do notation and with these functions, etc. So a function, for example, you can have a function from, I don't know, the flavor of the cake that you would like to do to the recipe, right? It would take the string or the string that represents the flavor. For example, you want a strawberry cake, right? And then it will produce a recipe for the strawberry cake, right? You did not bake the cake. The function only produced the recipe for the cake. Does it make sense? So this is what Haskell does with programs with this IO type constructor. Okay? You do not execute anything, you only construct programs. Okay, hopefully that made sense. Now, so we have this program. What if we want this program to be sort of an interactive loop? How to make this into a loop? We don't have loops in Haskell. We don't have whiles. We don't have for loops. So how would we deal with this? Recursion, exactly. So very easy. We just put main at the end of main. And that's it, right? So this is a nice tail call. So this will just repeat forever. Very nice. Now, let's actually shift to something a little bit more interesting for this program. Instead of just asking for the name, what we're going to do is we're going to build a very, very simplistic task manager. So we'll have the user input some comments to add tasks, remove tasks, print tasks, whatever, right? Or actually, yeah, actually we're gonna first do the very simple command, which is please exit this infinite loop. So how do you exit a loop? Break? We don't have break. There is no return, no break. Right. Exactly. So for the recursive call, we now, before doing the recursive call, we need to check, well, do we have to make the recursive call or not? So what we can do is we can introduce this local function called handle, which takes input, which is the string that we received using getLine, right? So handle, if we pass exit to it, then it just prints goodbye and does not call main, okay? On the other hand, if handle receives anything else, then we print hello name and call main recursively. Okay, does this make sense? So again, you don't have break, you don't have continue, you don't have return, anything like that. You don't have in Haskell. So this is how you do it. Okay, now doing this with a helper function is fine, but we can also do this case analysis directly whenever it needs to be done. So we can do this with case expression. So this can be used not only in the do notation, it can be used anywhere. It's just an irregular expression. So the syntax is case expression of, and then a bunch of cases. And for each case, we have basically a pattern and the right arrow, and then the body of what we would like to return if the expression matches that pattern. So in this case, if input is literally exit, so it matches with exit, then we again return a program that prints goodbye. If the input is anything else, we call it name. We just interpret any other input as just giving us name. And then we return a program that is constructed using do notation, right? And consists of two expressions. One prints hello name, and the other one calls main recursively. Okay, does this make sense to you syntactically and otherwise? Okay, very good. So yeah, here's the general form of case expression, which is very easy. So the main difference I would say between case and using a locally defined function is that with a function you can have multiple patterns for several arguments. With case, you only pattern match against one expression. So that's a limitation that you might want to keep in mind. Oh yeah, you can do, for every pattern, you can have guard expressions, like with functions. So, okay, so now we have this state, and again, let's make it into a task, let's make it into a sort of task manager. But before we do that, for a task manager, we will need to manage state, well, the actual list of tasks that we maintain, right, a collection of tasks. So if we have this recursive infinite loop and we don't have any mutable variables in Haskell, how do we add state to this program? Yes, so this is something that we have done before in simpler functions, right? It's like in some examples in Racket even, where we had helper functions with accumulator parameter, right? We had this with fold L. The idea is that if you want state in a purely functional program, well, unless you want to go into some more interesting stuff like software transactional memory, which is a kind of mutable variable, but safe. Yeah, the default thing is to just introduce an accumulator parameter. So we rename here main to run with, which now takes a state as an input. And then whenever we do the recursive call, we have now an opportunity to modify that state. Okay. So yeah, this is called the accumulator parameter, and this is what is typically used in functional program to emulate state. Okay, does this make sense? Very good. And so main is now just run with some initial state. So let's introduce some context. So our state is going to be just a list of tasks, and each task is going to be represented by just a string for simplicity. But of course, you can have more complicated types if you want. Okay. So our state is going to be a list of tasks, and we're going to be asking the user to input some comments to add tasks, remove tasks, print tasks, etc. So now, by default, if we do not recognize the input as a comment, we will just assume that this is the actual task that the user wants to be added to the list of tasks, right? So if we do that, now you can see that in the recursive call, we add task to the state by using the colon, the list constructor, right? Does it make sense? Not very complicated yet? Okay, just let me know when it becomes complicated, because I don't know where it becomes complicated for you guys. Is this fine? Moving forward? Yeah? Sorry, the question is, does getLine violate purely functional nature of Haskell? Okay, so again, getLine is a constant, but its type is not string. It's not a string, right? It's a program. The program that gets this line from the input does not change, right? When you execute this program, you might get different results, because the result of the program depends on, well, input output, right? But when you are doing this in Haskell, you do not have the immediately the result or the effects of this program. You only have the value getLine, which is just a program which does not change, which is the same all the time. All you're doing in Haskell is you're combining different programs into bigger programs, right, somehow. All of this is executed only in main. Okay, yeah, so basically, if you want to do imperative programming in Haskell, you can do it. You just have do notation and everything is fine, right? There are a few differences which we'll see in a minute, but generally it's completely fine. So as our first comment that is different from adding a new task will be to print tasks. Now, to print a list of tasks, we have as our input a list of tasks, and we need to produce a program that would output those tasks on the screen, right? So how do we do this? Well, whenever we have a function on lists and we don't know what to do with it, we always write two equations, right? Right? Which two equations? Yes. What's the base case for lists? Empty list, right? So we write always two equations. If we don't know what to do, we write two equations. One equation for the empty list, one equation for the non-empty list. Okay? Very good. So if the list is empty, well, then there are no tasks. So something that we can do is we can print, well, there are no tasks. Okay. Now, if there is at least one task, then, well, we can use the do notation to first print the current task and then recursively print the rest of the tasks. Right? Very easy, right? Now, of course, if we leave it like this, then we will always have no tasks as the last entry, right? Which is probably not what we want. So to sort of fix this little issue, we can add one more equation. If we have a list with exactly one task, then we just print that task. Okay. Okay, but this is a minor thing. Okay, but now that we have this implementation, right? Now that we have this implementation, we can look a little bit closer at it, and we can see that, well, really what we're doing is for empty list, we're printing no tasks, but otherwise we're just apply put strlen to every task in the list, right? But if you're applying a function to every element in the list, then which function should you immediately be thinking of? Map, right? So you would like to rewrite this as, again, two equations because the empty list is special case. But for the non-empty list, you would like to just use map, right? Question, would this work? Okay, so how many of you think that this can work? Anybody? I mean, seems like a trick question, right? Okay, so why can't it work? Yeah? Right, exactly. So whenever you use map, it always produces a list. Okay, so what it will be a list of? A list of strings? Yeah, remember that putstrlen is a function that takes a string and returns a program. So what you will have here is you will have a list of programs instead of a single program, okay? And so this is one of those places which are different from, say, doing the same thing in Python or in JavaScript, right? This is where you start feeling this difference between when your function actually performs something and when your function returns a program, okay? Very good. So, okay, we cannot use map. Well, how do we fix this? Well, if we have a list of programs, what we really want to do now with that list is to run those programs in a sequence, right? The first and the second, etc. Okay, so let's do that. So let's still keep that map and then apply a function called sequence underscore to that list. Now, this is one of the standard functions, but we're going to re-implement it here, right? So sequence underscore takes a list of programs and produces a single program by concatenating basically all of those programs together. Okay, how do we do this? Well, again, we have a list. Let's do a recursive function. If we have an empty list, we do something. If we have a non-empty list, we do something else. Now, in this case, it is actually easier to deal with the recursive case first. So let's do that. If we have at least one program, then it's very easy to sort of do the recursive call. We just run the program and notice that we have just taken this program from the list and we use this program as is, right, in the do notation, right? Because program is a program, so we can use it directly in a do notation. And then in the next line, we do the recursive call, calling sequence of the rest of the programs. So now the question is, what do you do for the empty list, right? Because what we are supposed to do is to return a function, a program that, well, what should this program do? It should do nothing, right? So how do you do nothing? Sorry? What? No operation command. Sort of, yes. You of course, since IO is implemented, the implementation of IO is hidden by the compiler because it's specific to the whatever compiler you're using. You still have functions that allow you to construct IO, right? You can use this do notation. Unfortunately, you cannot really, I don't think you can use an empty do notation, right? Because that, again, does not really make sense, because if you have an empty do notation, then, well, if it's a program that when you execute this program, what should be returned, right? You should always specify that. So what you do here is you do something that for you might be very confusing when you first see it. You do return empty tuple. Okay. Now this can be confusing mainly for the reason that return is a very, very bad name. I mean, it's an okay name in general, but because return is so widely used in common, in your favorite programming language, whatever it is, the meaning of return is sort of ubiquitously recognized as a statement, not as an expression, right? In Haskell, however, return is, can you guess it? Is a function, because we're in a functional language. Everything is a function. So return is a function, which actually works for any type. And what it does is it takes a value of type A, whatever type A might be, and it returns a program that doesn't do anything except for returning that value. Okay, does this make sense? Now, again, in a regular language like Python or C++, this distinction does not exist. You do not have a type of programs. So there is no need for this wrapping of a pure value into a program that returns that value. Here, though, it is very important. Okay, so yeah. No, because IO is a type constructor. You can only use it where you expect types. Here we expect a value or a term, right? We're on a different level. So yes, we cannot use just IO empty parenthesis because IO is a type constructor, not a value constructor. Right, so what's important, yeah, I don't have a slide for this, unfortunately, but since return is really just a function and return something is an expression, you can actually put it in the middle of the do block, right? But it is not a control statement. It is just an expression. It is a program that doesn't do anything and just returns some value. So if you put it in the middle of the do block, it will do nothing, return that value, be very much ignored, and then the do block will continue executing the next expression in the sequence. Okay? So please do not try to use return to exit a program, right? That's not how it works. Okay, very good. So now we have this sequence, and we can use it in combination with map to sort of apply this function which produces a program to every list, to every task in the list of tasks and print out all the tasks. Now, this combination of sequence and map is, of course, very, very common. In fact, there is a slightly more general function called map with a capital M and underscore. Its type is actually more general, and the type of sequence is more general that I'm showing to you. But for now, it's fine. We can just assume that everything is just IO. So map M will take a function from A to a program that returns a value of type B, right? Then it will apply this, this function to every element of type A in the list, do that IO something, and then ignore all of the results. Okay, basically only run for the effects. Okay, does it make sense to you? So underscore is just a convention to let you know that the result of the computation is ignored, only the effects of the input output are preserved. So there are of course versions without the underscore that preserve, that return the list of results. But yeah. Okay. Very good. So now we can just use map M. So instead of map here, because we're dealing with programs, we're using map M underscore. Slightly different map, but does the job. Yeah. Why do we not, what? take the input of which function? You mean recursive function? We did write a recursive function like this. Did you mean this? We did write this. You can write it like this, yes? This is a recursive function, explicitly recursive function, right? But again, so what happened is we wrote this function. We realized that, well, all that we're doing is we're just applying put_strlen to every task in the list. But that sounds like a familiar action. This sounds like a map function, right? So we would like to use map, but then the regular map does not work. There's a type error. Okay, how do we fix this? Well, the result is a list of programs instead of a single program. So now we have to figure out how to execute a list of programs. Well, to do that, we introduce sequence underscore, right? Which takes a list of programs and concatenates them all into a single program. Okay, very nice. But now that is completely fine. And I'm just taking a, yeah. You mean the first, you mean that we could remove the first equation for print tasks? Okay. Well, if it's empty, then what? And if it's empty? We don't do anything. Well, then if you run this function, right, it will run recursively. So the question is, if you do not write this first equation for sequence underscore, right? Because you don't like return, or for example, right? If you don't write the first equation for sequence underscore for the empty list, then if you call it on any list, recursive calls will eventually get to the empty list at the end, right? And then your function is undefined on empty list. So what you will have is you will have a runtime exception, which is not very nice, right? Especially not in a purely functional language where you're not supposed to have those. Okay, very good. So now that we have print tasks, we can put that back into our original program. So we just add one more case into our case expression. If input is print, then print tasks with the current state, which is the list of tasks, right? So fairly straightforward. Now, these are commands without any parameters, right? You can have complicated commands that do complicated stuff. And dealing directly with strings is typically not considered ideal in any language, right? So what you typically want to do is some way to convert from strings to some sort of way to understand if this is a valid command, and then go from that command to actually executing that command. In Haskell, with some types, we have a very neat way to do that. We can just introduce a type called command, which will list as different alternatives possible commands. So this is one of the nice use cases for the sum type. So one of the possible commands is print tasks. So we have a constructor for that case. Another possibility is add task. In that case, we have an actual task attached to that. Right? Now, I'm going to complicate a little bit our state. I'm going to add task identifiers to every task, but that's not very important. I'm only doing this to sort of be able to add more commands. Like, for example, we can add remove task that would take task ID, right? And we can also add exit. We had that command as well, right? And you can, of course, add any other commands that you want. okay? The point is, some types are a really neat way to list exactly what comments you have and how many arguments of which types they have, okay? By the way, what would you do in a similar situation in your favorite programming language? Yeah, that's one idea. That's, for example, how you would do some sort of remote procedure calls with JSON or whatever, right? That's how you would encode this. Yeah. So, okay, think about it. Maybe let me know later what you would do in this situation in your favorite language. Okay, so now that we have this data type, what we can do is we can go from the string, which is the user's input, to comment, right? Before we are processing or handling these commands. Now the question to you is this a good type for parse comment? Yeah, yeah, exactly. So one of the typical concerns that you should have if you're writing a function that parses something is, what if is not able to parse whatever I give to it? And again, we're not in Python where you ask for forgiveness, not for permission, right? Here, you will not be thrown any exceptions. So you have to think what are the possible outcomes, right? Of course, you can adapt for them later, but in this case, this is very easy to predict. We should use something at least maybe comment, but maybe something even more complicated that would give us an actual parsing error that the user is able to decipher, right? Okay, so parsing comment. So we have an input, and now parsing this comment, I'm going to use a case expression instead of several equations for parse comment because that saves me some typing. So words function is basically splitting a string using spaces. So this is, you have probably a split function in Python, I think, does that. And in JavaScript, there is also, I think, split or maybe some similar name. But anyway, so it's a common function that just splits into words. So why do I do this? Well, because it makes it easier to talk about the command and then its arguments. So if we have just one word and this word is print, then the command is successfully parsed, which means I use just, right? And the result of the parsing is print tasks, command print tasks. If I have the word done, or remove, I guess, could be also. So done would correspond to remove task, and it takes as its argument an identifier of the task. Now, of course, words returns a string. An identifier of the task is declared as an integer, right? So for that, I will be using a function called readMaybe, which has this type. Now, this type reads as follows. It's a function from string to maybe, A, for any type A that is an instance of type class read. Now, type classes we're not going to cover in this course, too complicated, but basically they are similar. You can think of them as something close to interfaces in Java. Okay, they're much better than those, but you can think of them as better versions of interfaces in Java. So read A tells you that there is basically a parser somewhere for this type A, right? And read maybe basically is a parser for this type A. So read maybe of ID string will return either in this case, either nothing or just some integer. So if parsing of this integer fails, well, we have an invalid identifier. In that case, parsing of this comment fails and we return nothing. On the other hand, if we do have a successful parse of that integer, we give it a name task ID, and the result of the parsing is going to be just remove task of task ID. Finally, if it's not print and it's not done, oh, I forgot to parse exit, but you can imagine that I did not forget it. And at the end, of course, if it's not print or done or exit, then whatever else, I just interpret as adding a task, and I just do that. Okay. So now that we have a function that takes a string and returns maybe comment, what we can do is we can, in our main function, well, in our run with function, we take an input from the standard input, get line. Then we do case on parse comment of input. Yes? Yep. What's the question? Yep. Yes. Yes. It will pattern match against the last case. Yes, not the done case. That's a good catch. You can fix that, and that is. But again, I didn't want to write a lot of equations here. But yes, you're correct. You have to be a little bit more sophisticated here. So case parse comment input off. So if the comment is not successfully parsed, then we can print, yes? Yep. So case off, between case and off, you have any expression. And you're pattern matching the result of this expression. So this means that you apply words to input, you get a list of strings, and then you pattern match that list of strings. Okay, makes sense? Yes. Well, that's a very good question. The question is, how does the compiler understand that read maybe is actually has to use the type int and not some other type because it's polymorphic, right? So the way it knows that is because we are using the result of read maybe, in particular task ID, when we pass it to remove task, right? But remove task only accepts integers, right? It accepts task ID, which is a synonym for an integer, right? Does this make sense? So this is one of those, again, nice places where you don't have to specify any types and everything works out very fine. Yes. Yes. No, task ID is an integer. ID star is a string. Task ID is an integer. Why is task ID an integer? Because task ID is an argument to remove task. And remove tasks are type, the type of the argument to remove task is task ID, which is equivalent to integer, right? So we know that task ID variable should have type int, right? But that means that the result of read maybe should be of type maybe int, right? And that's how the compiler knows that read maybe should be working for ints and should be parsing an integer. Okay. Very good. So again, parsing comment, parsing input, if we had nothing, the parsing fails, we print that, and we recursively run with the same state. If we have just exit, then we print goodbye and do not have any recursive call. If we have print tasks, Then we print tasks and recursively call run with. If we have add task, I forgot the parentheses, but again, you can imagine that I did not forget them. Then we print that there is a new task and we add it to the state when we do the recursive call. And if we have a remove task, again, imagine that I did not forget the parentheses, we call some function. I did not implement it, but you can imagine that I have. And then we get a new state where this task is removed, and we run recursively with that new state. Around add task, new task, and remove task, task ID. There should be parentheses. Let me show you. Around this and around this. Because just has one argument, not two. Okay. So this is how you can do this pattern matching. Now this is nice, but you can recognize that, I mean, this is a simple example, but we already have a lot of code duplication, right? Like these recursive calls, and we have to remember to not forget put them there, because otherwise our computation will just stop after some command, right? So what would be nice is to have a sort of generic handler for these commands. So we start with this type. Handler is defined as a function that takes the current state and then returns two things. First, it returns whatever we would like to say to the user. And the second thing is maybe state. Now here, if we return state, then it would mean that we just update the state and move on. If we return nothing, that would mean that we would like to stop the program and not do any recursive calls. Does this make sense? So now for every command, what we can do is we can implement a corresponding handler. For example, to print tasks, we can define a handler which would take state and return just the same state together with pre-printed state, which is just a list of tasks. Now here, we're basically doing the same thing as with print tasks, right? But this time, we're not using input output. We're simply generating the string that will later be output. Okay, so here in this definition of a handler, we are avoiding input output, and instead we only encoding what is strictly necessary to provide by any handler of any command. Does it make sense? So again, this is a simplified example, but bear with me. So now we can do the same for add task, for example. In this case, we take the new task and return a handler. And remember that a handler is just a function. But when we have an argument and return a function, it's the same as taking two arguments, right? Because all functions in Haskell are secretly functions of one argument. So when we take a task and return a handler, it's the same as saying, okay, handle add task takes new task and returns a function, which means that we can, again, take one more argument, which is the state, and then return the result, which is some response, which in this case is just saying new task, and then the new state. And the new state just adds the new state, the new task to the state. And similarly, we can define handle remove task and handle exit. Does this make sense? Very good. Now, once we have that for each command, we can have a single handle command defined, which takes a command and returns a handler. Okay, how does that work? Well, if the command is exit, we return handle exit. If the command is print task, then we return handle print tasks. Right? Note that we are returning functions here. Does this make sense? Okay. So this should be very straightforward, because each command that we have should match exactly to some handle command function. Very good. So this is very straightforward to write. Now we can use this in our run with function. So what changes? So everything is the same for the nothing case. But now if the parsing of a comment is successful, we have a comment, and instead of pattern matching on different comments, we can now just simply handle comment. Now handle comment, and I forgot here to pass an important bit of information. So this is a handler, which is a function, right? So we have to pass here the current state to the handler to get the response and the new state. But now that we have the response and new state, we can just print the response and run recursively with the new state. Right? And again, there is one tiny mistake in there, but I will fix this in the slide and re-upload. The idea is the same. So you use this handle command to dispatch of which handler you're going to use for this particular command, right? Run this handler, it will return the new state, it will return the response, and you will just print the response and update the state and run recursively. Now, what's good about this approach is that in our handlers, we don't have to do these recursive calls. We just process a single command, do whatever we want, and that's it. And all the recursive calls and handling the state and everything else, and even parsing, is all within this run with function. Does it make sense? So what we have done is we have put all of our input output in this single function run with, and all of our logic, what's typically called application logic or business logic, right? It's all now in pure functions. Okay, why would you want your application logic as a pure function as opposed to an executable program? Formal verification, well, you can formally verify lots of things, including executable programs. But yes, it is generally easier to verify purely functional code. But it is also easier to test purely functional code because pure functions are deterministic. They return the same output given the same input. If you have an executable program and you want to test it, well, it might depend on the state of the database, right? And if it is the case, then it is very hard for you to test it properly if the database changes, right? So you have to sort of manage the environment accurately enough. And in many applications, you don't have just, you have a logic that can actually interact with different resources. And so it's the same logic, but it can work with a database, with a local database, or with a remote database, or with a remote server, or it can interact with some local cache, or whatever, right? It can get commands via the command line, or via web interface, or via, I don't know, remote procedure call, or whatever else. The logic, if you want to test the logic that it works correctly, if it is pure, it is much easier to test, it is much easier to debug, it is much easier to handle. So in general, when you are using functional programming, even if it is not Haskell, even if it is Python or JavaScript, the general tendency is to put application logic into pure functions. And you can even find this like in many JavaScript frameworks, they still use this accumulator parameters even, or even if they do not use recursion, they have still extra parameters for this, for the state or configurations. So again, what we have done here is we have separated IO from the pure application logic. And now the final state that will bring this to something that you could recognize is, well, we have this parse command and handle command, and all of the application logic is contained within those two, right? So if we just parameterize over those, put them into arguments, the now run with actually takes two functions as an input. One that parses the comments and the other that handles the comments, right? But now when we do this and we expand the what handler is, notice that nowhere in the code of run with do we depend on what actually is the type comment or what is the type state. The code is actually parametric, not just over the functions themselves, but also over the types of comment and state, which means that instead of comment and state with a capital CNS, we can use them with the lowercase CNS, meaning that these are type variables, which means that this is a function, a generic function for interactive programs with comments and state, which can be entirely determined by the user. Okay. Now, this should be familiar to you because of things like activity off in code world. This is essentially how it is implemented, except, of course, a little bit more complicated than that. But the general idea is this, okay? So hopefully this is a little bit of design that you take away with you, and maybe you can see it in other frameworks and other languages. Okay, thank you. Sorry for keeping you a little bit late. See you.